Forget frequently asked questions.
Common sense, common knowledge, or Google.
How about advice from a real genius? 95% of people in any profession are good enough to be qualified and licensed. 5%
Go above and beyond.
they become very good at what they do, but only
0.1%.
are real geniuses. Richard Jacobs has made it his life's mission to find them for you. He hunts down and interviews geniuses in every field: sleep science, cancer, stem cells, ketogenic diets, and more. Here come the geniuses. This is the Finding Genius Podcast
With Richard Jacobs.
Hello, this is Richard Jacobs with the Finding Genius Podcast. I have Vlatko Vederal. He's a professor at the University of Oxford. He works on quantum information science. So, Vlatko, thank you for coming. How you doing?
I'm doing really well. Thanks a lot for inviting me.
Yeah, I know, a little bit about quantum mechanics and quantum type issues, but what is quantum informational science? What's that about?
Quantum information science is about upgrading all the existing technologies that rely on the laws of classical physics, really, into the quantum realm, which is the realm that is obeyed by small objects like atoms and molecules and particles of light, photons, and all of that. And what we are trying to do is encode bits of information, not into large systems like conductors, for instance, but we're trying to go down to the level of an individual atom. And of course, the laws of physics completely change from classical to quantum there. And instead of just having two different states which encode one classical bit, we now get infinitely many states, if you like, which is what we call a quantum bit. So a quantum bit can be in two different states at the same time, which is really the key difference between quantum and classical information.
So how do you think a transition from current computing would go to quantum-based, architecture? Is it the storage first would be, secured, let's say, by quantum cryptography? Would the transmission happen first? What order do you see things happening in?
Yes, I think the easiest thing to do, as you said, at least as a proof of principle, is quantum cryptography. Because this really relies on either sending individual quantum bits between two places or sharing entangled pairs of highly correlated quantum systems. But we're still talking about two quantum bits at a time. And of course, it's much easier to manipulate this, which would involve, let's say, thousands or even millions of quantum bits. So certainly we are talking in this near future term, we are talking quantum cryptography. We are talking possibly some memory, quantum memory, storage. But even then, we're talking about a very small number of quantum bits that we can store. And then probably one day within maybe next 10 years or so, we will talk about large-scale quantum computers.
So how would quantum cryptography work? And then I want to ask you about transmission of information.
Oh, yes.
If we can go into it.
Yes, I think that's the key issue there, which is this property that I mentioned of quantum bits, that they can exist in two different logical value at the same time. So you could have a logical 0 and a logical 1 simultaneously in what we call a superposition of states. So, if you're thinking about an atom that you could use as a quantum bit, you'd be thinking about two different energy levels of this atom as your two possible states. But of course, quantum mechanically, you could even have a superposition of these two energy levels. Now, the key issue in quantum physics is that if you were to make a measurement on this state, then quantum physics says that you would randomly get one value or the other value, and there is a probability which is assigned to this event. And so what this means is that if two people are trying to communicate using quantum bits, then anyone who is trying to eavesdrop on this communication is actually forced to make this kind of measurement, and is forced to collapse this quantum bit into one of these two classical values. So the key thing is that any eavesdropping of this kind would actually be detectable within quantum physics. So you classically, of course, you can eavesdrop in principle and stay unnoticed. But because of this property of superpositions in quantum mechanics, whenever you make a measurement, you actually collapse this superposition to a classical state. And when an eavesdropper does something like this, then the users of quantum cryptography protocol could actually detect that someone was intercepting the message and trying to eavesdrop.
But the act of receiving, a message in the quantum state would decohere it. So I guess also too, it makes it short-lived because you have the transmission time, but then as soon as the recipient receives it, they're collapsing it, the coherent state in order to interpret the information being received, right?
Yes, you're right. So this is a beautiful point that you are making there, that actually even the recipient of quantum information has to decohere it. So when Alice is sending a quantum bit to Bob actually has to make a measurement, because otherwise you have this confused superposed state. And of course, the key consequence of this really is that you will have to use many quantum bits, and you would have to repeat your communications, so that by making a sequence of measurements, Bob can really get a definitive result. And so on the one hand, you suffer from this decoherence, as you say, from the collapse. But on the other hand, the advantage that you get is that anyone else trying to do the same in between these two, the sender and the receiver, would also have to do exactly the same, and therefore could in principle be detected. So, you pay the price of a slower protocol, if you like. So the bit exchange rate in a quantum protocol would be lower than the classical. But on the other hand, you can guarantee a higher degree of security than anything that's classically possible.
But if you try to attack or perturb the system or measure it continuously, poll it, every nanosecond or whatever, would you also stop the transmission of information, because that's needed to do so securely?
A very good point as well. So basically, you would do this with one quantum bit at a time. And then you could reuse this bit, but you would have to re-prepare it in a quantum state. So you're right, you would first prepare a quantum state and send it across. Then the person making a measurement would collapse it. So in that sense, you could not reuse it again in that very state that's collapsed, but you could prepare another quantum state and then send it back again to continue the protocol. So the whole protocol would be a sequence of preparations of quantum states, then sending them through a channel, and then making a measurement that would collapse it back into a classical state. And then you would have to re-prepare this in a quantum way, send it back, and so on. So you're absolutely right. What you want to ensure is that there is no other collapse than the users of this protocol. So you don't want any environmental noise, any other noise, any eavesdropping would, of course, be detrimental to this protocol.
Well, could you use a quantum encrypted envelope so that would be the subject of attack, and then the inside information would never be gotten to?
Yes, that's true. You could somehow use a protective quantum system. Again, you couldn't really protect anything better than you can try to open this envelope, as you said, and read the message inside. So the key thing is that you cannot prevent an eavesdropper from blocking your communication. So an eavesdropper can really catch all the qubits and decohere them, and therefore they can certainly spoil your transmission. But the bottom line is really that they can never do that without being noticed by the recipient and the sender of the information. So it's possible to encrypt it, as you say, quantumly. And again, the advantage would be that any eavesdropper would in principle be detectable.
And I guess if you had a layered envelope system, you would know, okay, we're being attacked or being sniffed, maybe have time to trace it or, move to an alternate communication system.
Exactly right. So that's how this would go, that you would say you would measure the bit rate and you would realize, for instance, that the fidelity is lower than what you're prepared to tolerate. And that would automatically alert you to the possibility of an eavesdropper being there, which means that you could just abort your protocol and, as you say, switch to another channel, another mode of communication. That's exactly how this would work in practice.
Well, how much information can be transmitted in one bit at a time? How fast or how slow would it be?
Oh, good. That's another good point. That really depends on the quantum, how you encode your quantum bits. The fastest, of course, would be to encode it in photons, in light, because you travel at the speed of light, which is the fastest possible speed according to the laws of physics. If you were to encode it into systems that have mass, like atoms or even electrons that are much lighter, they, of course, would have to move slower than the speed of light. And of course, how quickly they move depends on the amount of energy that you would invest into this protocol. So the ideal case scenario would really be to send photons between the sender and the receiver. And then, of course, the second part of your question is how many photons could I really send per second, let's say. And this again depends on how cleanly you can produce these photons. So for instance, you could in principle produce a single photon every femtosecond. So that's basically 10 to minus 15 seconds. So you could produce 10 to the power of 15 photons per second. This is not something we can do now, but in principle, the laws of physics would say you could send as many messages per second as the number of photons you can produce, which would be very rapid. Of course, these days, our transmission is much, much lower than that because the fidelity with which we can produce a clean single photon is not as high as this. So we're required to produce many more photons as a part of kind of error correction in order to get one clean quantum bit. But in principle, you can send a lot of quantum bits per second if you go down to the level of what physics really allows you to do.
Oh, okay. So you can still send a substantial amount of information quick enough.
Very, very substantial. I think at the moment we are extremely slow, like I said, and that's because we are limited by the current technologies. So, you'd be looking maybe into 1,000 quantum bits per second, which sounds ridiculously slow compared to the communication that we are even using now, the classical channel. But in principle, this could be billion times faster, or even more than that. So it sounds very good what physics offers you there.
What about using entangled systems, and then there is no transmission, right? Or it's, I guess physics thinks that it's either instantaneous or there is no transmission somehow.
Yes,
but it still gets there.
That's right. Somehow with entangled systems, you are investing all the work ab initio, you're putting it into the preparation of these entangled systems. And maybe that's the challenge there, that what you want is you want to maintain this entanglement over the distances that separate the sender and the receiver. And again, we spoke about decoherence earlier. Anything in the environment that interferes with these photons could, in principle, collapse, could decohere this entanglement. So somehow maintaining entanglement is much harder than sending individual quantum bits. But again, the upshot of that, the advantage of that is that you really get the most secure form of quantum communication that you can get. So I think when you talk to the practitioners in quantum cryptography, using entangled quantum bits is the preferred option, certainly in terms of security. But then again, you are paying a price in terms of robustness of this because it's more susceptible to noise and decoherence.
If you like this podcast, please click the link in the description to subscribe and review us on iTunes.
When you entangle, two particles or two systems, do you then have to move one of the entangled particles to the target location, or how do you?
Exactly right. You can entangle them in one place, as you said, you can produce them locally. And this again depends on the technology that you are using. But with 2 photons, for instance, what would happen is you would use a piece of crystal that has a property that when you shine some light onto this crystal, it tends to emit photons in pairs. And they are really these entangled pairs that people have been using in all our current optics experiments. Now, when you get that pair produced, you would have to make sure that one of these photons goes to the sender, if you like, and the other goes to the other location, to the receiver. So they would have to travel all this distance in order to be used for quantum cryptography. Of course, alternatively, you could think of the sender creating the entangled pair and then sending one of these 2 particles to the receiver whilst keeping the other particle. So that's also possible.
Oh, that seems like a lot of work to communicate.
Yes, I think that's exactly the bottleneck of this, is how many entangled pairs can we really exchange in this way to set things up? Because once you set them up, of course, you can just implement the protocol. But the tricky bit is really generating a large number of entangled pairs and making sure that they remain entangled and stable before your communication starts.
So for right now, at best, do you see a hybrid system coming where, we'd have traditional fast communication through a network, but again, maybe you'd have quantum encrypted envelopes that would, sense any intrusion?
Yes, I think again, people talk a lot. The word that you use is exactly what we discuss these days, the hybrid system. So you're still gonna rely on a very heavy classical information processing. But then when you encounter parts that can be improved quantumly, that can be sped up just by using a very small number of quantum bits, then you switch and do that kind of as a subroutine on a quantum computer and then bring it all back onto this massive classical parallel computation. So I think at the moment people are envisaging no more than, let's say, 100 quantum bits, which are very clean, high fidelity, and then coupled to a conventional, fast classical computer that would actually do the bulk of this work. And we don't know really when we are going to go beyond this level. We might be in this hybrid domain over the next 10 years before we really figure out how to scale up quantum computers and make them more stable.
Interesting. What do you think is possible, I guess further out in the future? What would a really advanced system look like to you? What would it have?
Oh, I think an advanced system would be really amazing, because you'd be talking, I think already with more than 1,000 quantum bits, you could really do computations that cannot be done with all the classical computers put together that we have currently. So we would have a huge exponential increase in terms of both the memory, the capacity, as well as the speed of computation. And I think the interesting thing is that we are now thinking frequently of computation as classical input. We give our computer some classical data, then the computer does its work and processes this, and then it gives us back classical output. What a quantum computer could do actually is something that a classical computer wouldn't even understand, of course. So it's not just about the speed of information processing, but it's about the quality of what kind of information is really processed on this device. So a quantum computer would be able to operate, to act directly on a quantum input. So you could be able to put an input, which is an entangled state of quantum bits, then you process it on a quantum computer, and then your output could again be a genuine quantum state. So this is something that a classical machine would not even be able to understand. It just wouldn't be able to handle this kind of information processing. So that's where I think the field is going. And if you talk to a physicist like myself, I think we're really excited about simulating more and more complex systems. We can go with these ideas into chemistry, into biology, certainly, but people are already investigating simulating complex financial systems, for instance, or weather patterns, all sorts of things like that, I think would become more tractable on a quantum computer.
I've heard that errors could be a big problem with quantum systems. How are people trying to control for error rate and error propagation right now?
Yes, I think there are two aspects of that. That really is the main issue, as you said. How do we control these errors? Because a quantum bit being in a superposition of two states, it's enough that it couples a little bit to its environment to actually result in the decoherence and effectively to the reduction of all of these quantum advantages to the simple classical computation. So at the moment, whatever qubit technology we have, it seems to me that error rates are simply too high for us to be able to scale this up. So in some technologies, we can handle a small number of quantum bits, up to 10 quantum bits really well. But then because these errors simply multiply exponentially, the more qubits you get, the exponentially bad, decoherence also gets. We really don't have a good, stable enough medium that we can use directly to make quantum bits. So what we're forced to do at the moment is really isolate our systems from the environment. So what this entails, for instance, just to give you an example, is taking an atom and cooling it down to a very, very low temperature, colder than a billionth of room temperature, so 1 billion times colder than the room temperature that we are all used to. This is something that you need to do in order to achieve a certain degree of stability for this atom to become a high fidelity qubit. And of course, the problem is that as you add more and more qubits into this system, they get hotter, noisier, and it gets harder to actually keep them at a very low temperature at which they need to be. So so the only solution we have for this currently is to do error correction, which means we add even more atoms. We add a lot of redundancy there. So instead of having one single atom as a qubit, we have 100 atoms all simulating one logical quantum bit of information. So there is a huge redundancy. For every logical qubit, we would need another 99 physical atoms to encode this logical qubit properly. And we don't really know. We know how to do this in theory, but we don't know how to do it in practice. The other possibility, which I think is also fascinating, is if someone could really come up with a system that's fully quantum and exhibits all of these superpositions even at high temperature. So for instance, if someone came up with a room temperature superconductor, so a substance that would superconduct even at the room temperature that we experience, this would automatically become the top candidate for quantum information, because it would be stable without having to invest any extra work into it. So this would be a breakthrough technology, but again, we don't happen to have anything of that kind at present.
Okay. Well, very good. Vlatko, what kind of timeline do you expect that, consumers will experience any of this technology? Do you think it's still a long way away, or are we getting close on some aspects?
I think we're getting closer. We probably from 2000 onwards, there really has been a huge increase in both investment into quantum technologies. And what's exciting, I think, is that initially all of this investment was basically governmental, I would say, up until maybe 3 or 4 years ago, when industry and some really heavyweight players started to get engaged. So now you have Google and Microsoft and all sorts of other actually a huge number of startups as well, all using different platforms to encode quantum bits. And I think since maybe 3 years ago, most of us have really become much more optimistic that this would happen sooner rather than later. So I think, I really think, at the moment, of course, what you can do, and I think this is in the public domain, you can actually use some of these IBM machines, for instance, cloud quantum computers, but these are not very clean qubits. And I think you will never be able to use more than 20 to 50 quantum bits. So they're not even proper quantum bits. It's very hard to predict how quickly this will evolve, but I'm guessing that within a year or two, we will have 100 clean. When I say clean, I mean fidelity 99.9%. We will have 100 clean quantum bits. And I think then we can already start to do something very exciting. Going beyond that, with 1,000 quantum bits or 1 million quantum bits, we are certainly talking about 10 years and beyond. But I'm personally rather optimistic about this. And I think these technologies, when do they really become publicly available? It's really extremely hard to predict. When are we going to have quantum laptops is the question. And I think we are looking we are looking at maybe 20 years beyond. But it sounds to me much sooner than what we would have predicted even 20 years ago.
Well, just last question. I know I should have asked this earlier, but what I know there's various ways to create qubits. What are some of the ways that you know of, and maybe some of the trade-offs between the ways? Using loops of wire to and using currents to make qubits versus trapped ions, etc. Can you describe a few of the ways that in which qubits are made, and maybe some of the advantages or disadvantages of them?
Yes, I think you already mentioned the key. There are three key technologies that people pursue now. Superconducting qubits are possibly the most appealing to people in industry. And I think there is a reason for that, because this is a solid state domain technology. So, of course, all our classical computers are based on semiconductor technologies. And when you talk about superconductors, they are actually quite easy to integrate with the existing classical architectures and classical computers. So it seems to me that the reason why the industry, if you think about, Microsoft, Google, and IBM, if you ask yourself, why do they prefer superconducting qubits? I think it's simply because they arise very naturally and they can be combined very naturally with the existing classical technologies. That being said, a huge disadvantage of superconducting qubits, so here you're using a lot of electrons that can be moving in one direction or another direction. So you're talking about electrical currents that exist in two different states simultaneously inside the superconductor, and that's your quantum bit. The downside of this is that it's very hard to get a high fidelity superconducting quantum bit. They're really very noisy. If you look at the current computers that are on offer, already with 10 to 15 qubits and applying maybe less than even 100 gates to these 10 qubits, your noise will be so large that your computation will effectively be all but classical. So superconducting qubits, easy to integrate with the existing technologies, but very hard to improve as far as the fidelity is concerned. So scaling them up is not clear at all. Ions would be the preferred option to a physicist if you really want an ab initio clean qubit. So we know how to control a single cold atom with a 99.9999% fidelity. This is 6 nines. So it's certainly a high enough fidelity that error correction could also in principle be applied to them. But of course, what's difficult with these technologies is that you have to engage lots of cryogenics. You have to keep them cool, and this requires an awful lot of equipment, which comes completely as a new form of equipment, very different to anything we do classically. So ions would be the cleanest qubits in that sense, But the downside is that they are very hard to integrate with the existing solid state devices. And finally, the third technology that people are pursuing are photons, simply using light to do quantum computation. And again, this has a bit of both of these technologies. In some sense, you could see how you can generate lots of photons, how you can do certain operations with them. But producing highly entangled states of these photons may actually be a big challenge. And there are a few startups working on this that looks extremely exciting to me. But again, even going beyond, 10, 15, 20 photons with high fidelity, it's very, very hard at the moment.
What level of fidelity is really needed? I mean, 99.9 to a regular person probably sounds like, whoa, that's great fidelity. But
yes.
Do we need 5 or 6 decimal places of it, 5 or 6 nines in order to be commercially viable? Like, what is needed?
Yes, I think the question really depends on how many extra qubits you really need to engage in order to be able to error correct. Certainly, anything above 98% suffices in principle to scale it up. But what you gain by improving the fidelity of even individual qubits is that you need less redundancy in order to scale it up to error correct. So of course, ideally, you want to be in the limit where every physical qubit is also your logical qubit. You almost don't need any extra redundancy. And for that, you really need to go beyond what we've been discussing. But certainly anything above 98% already gets you into the regime where you can do quantum error correction.
All right, so the systems are superconducting qubits, trapped ions, and what's the third one?
Photonics, pure photons, basically just using light, using individual photons to encode qubits in different degrees of freedom.
Oh, what's the upside and downside of doing that?
The upside maybe of doing this is that it's not difficult to produce these photons. You can almost produce single photons on demand these days. You can excite a molecule, and then as the molecule emits, it will emit a single photon in some regime. So it's very easy, relatively easy compared to ions. Let's put it that way. It's relatively easy to produce photons, but what's really difficult with them is that it's very difficult to get them to interact with one another. So doing logical gates with photons is difficult. So in some sense, you can achieve a certain degree of noise robustness. And it seems to me this is possible with photons. But what's difficult then is to make an efficient sequence of gates with photonics. So I think no one really believes that photons on their own will be the ultimate qubits. It could be that photons will be used for communication between different, let's say, ionic qubits or superconducting qubits. But on their own, it's unlikely probably that we will have all photonic quantum computer.
Okay. Well, very good, Vlatko. What's the best way for people to find out more about your research and to follow up with you?
The best thing is probably to go on my website, and I think there will be a description of the research that I do. It will describe maybe 4 different areas, all within quantum information and computation that people can explore. And this is both on the theoretical as well as experimental side. So probably the best thing is just to Google my name and they will come to my research website, and then there will be quite a lot of information there. Of course, if they want to go beyond, then they're welcome to just email me and ask me directly about it.
Again, for listeners, your name is spelled Vlatko. And last name is Vedral. Got it.
Perfect.
Okay, Vlatko, thank you for coming on the podcast. I appreciate it.
Thanks a lot. Pleasure. Thank you.
If you like this podcast, please click the link in the description to subscribe and review us on iTunes.
You've been listening to the Finding Genius podcast with Richard Jacobs. If you like what you hear, be sure to review and subscribe to the Finding Genius podcast on iTunes or wherever you listen to podcasts. And want to be smarter than everybody else? Become a premium member at findinggeniuspodcast.com. This podcast is for information only. No advice of any kind is being given. Any action you take or don't take as a result of listening is your sole responsibility. Consult professionals when advice is needed.